In a pressurized water reactor, if a pump breaks, you can like turn off the reactor. The induced radiation in the water goes away after like 7 seconds. And you can walk in there and do some maintenance on the pump. You can pull the pump motor, you can fix a wire, you can adjust the thermocouple, and you can walk back out and turn that reactor on. Can't do that in a molten salt reactor. The pump is so radioactive, like it's absurdly radioactive. Like I don't think people understand the like 8 orders of magnitude of radiation that are around and operating a reactor that has fission products. Even after you shut it down, you can't go anywhere near it because, again, all the fission products are in there decaying away.
A warm welcome back to Decouple. Today I'm joined by fan favorite and returning guest, Nick Touran. Nick, welcome back. Good to have you here.
Thanks. Always a pleasure. Thanks for having me.
So I feel like you need no introduction, but I'll just rattle off a few things. Obviously, you are the bright mind behind the What is Nuclear website, which I think is really one of the world's foremost platforms in terms of science communication with regard to nuclear power. I know it's been a great resource for me. You also have a PhD specializing in neutronics, I believe. And you spent a career really in the advanced nuclear space. So today, you're on to talk a little bit about molten salt reactors. Really excited to have you. But first off, anything else to add to the illustrious introduction?
Not really. I think you covered it. Yes, I just wrapped up 16 years at TerraPower, and I'm now there's a brand new What is Nuclear LLC that I'll be doing full time at least for a few months, and we'll see how it goes.
Yeah, I mean, the other thing, of course, I should mention is you're kind of like the nuclear historian guy. You digitize films of a whole bunch of interesting experiments at national labs, Camp Century, the famous microreactor not just a microreactor, it was the reactor powering a whole camp. I was just building a big snow shelter with my son. We had a dump of snow up here in Canada a few weeks ago, and watching the digitized film you got out there of Camp Century, it was pretty fascinating, just on a grand scale, making just a kick-ass snow fort.
Yeah, that's got to be my favorite film. In fact, that film, which someone else digitized, inspired me, and I was like, what else is in there? And so I went and found there's like hundreds of other films along those lines for different reactors, but still that one with Muckluck, the Husky, is still probably like the best one. But I can't take credit for that one, but yes, I've done maybe 25 others with, help and sponsorship from just volunteers through LinkedIn and stuff. And there's some really great stuff. In fact, I have 12 new ones coming out soon. They'll be a little technical, but they're going to be about like sodium experiments, sodium equipment from the Clinch River breeder reactor. So those are going to be hitting hopefully next week or something like that. So more on the way.
Yeah, I mean, they're fascinating, like historical documents from this moment, I guess, in the 1950s and 60s, where there was this extraordinary amount of exciting research happening in the nuclear space, all sorts of different concepts being tried out. The films themselves have a certain sort of aesthetic, and I don't know. I mean, it's U.S. Army or National Lab type soundtracks, but they're very perky and peppy, and there's usually some bugles in the background and things like that. I was watching one just prepping for this interview on the molten salt reactor experiment, and again, that's the topic of the day: molten salt reactors. I love sort of starting off with a little bit of historical context. We've got a lot to dig into here. This is probably the world's most popular reactor. If there was a popularity contest going on, I'd say, endorsed by political figures like Andrew Yang, famously, but gets a lot of hype, gets a lot of downloads on YouTube. That's not what we're chasing here today. But we want to kind of understand this better because I think there's a paradox. It's maybe, when people think about nuclear, it's something that comes up top of the list, perhaps, but probably bottom of the list in terms of technology readiness level. And we've got to talk about why that is, about some of the grand conspiracies, et cetera, and just get, I think, a more balanced, realistic sense of this, phenomenally interesting technology.
Yeah.
I don't know what your starting point is. I think like the aircraft reactor experiment, like might be where it all begins, or even just looking at liquid fueled reactors in general. But
Yeah, I mean, I
take it
think
away.
we'll start with the liquid fuel and go straight into the aircraft reactor experiment. So yeah, I can just kind of tell the basic story of how that all got started, and you guide me along the way, keep me on track.
Sounds good.
Yeah, so I mean, you're right. The idea of a fluid fuel reactor is so popular, and it's one of the first things anyone asks me when they find out I'm a nuclear engineer. They say, "Oh, fluid fuel reactor," and there's an association with thorium, which we'll get into as well. But the first fluid fuel reactors were made in the Manhattan Project. They were called the water boilers at Los Alamos. They were basically an aqueous solution, like water with uranium dissolved in them, that would just boil water. And they did all sorts of early sort of nuclear experiments. They learned what the probability interactions are of different isotopes, using those as sort of basically research reactors. It's kind of scary to have high pressure radioactive fluid with water in it, which is also very corrosive. So we did build a series of reactors called aqueous homogeneous reactors, which were fluid fuel with some kind of uranium water solution in them. But they never really took off. There were a few at Oak Ridge that were built, the homogeneous reactor experiments 1 and 2. They were an attempt to make power, but they just kind of didn't work that well because of the corrosion. They kept burning holes in the vessel and dumping out all the fluid.
So just that I understand, like you're saying, you're dissolving enriched uranium in water. The water is the moderator, and it's just kind of a kettle that's boiling itself, and there's just fission products going everywhere, and it's under high pressure. And
yeah, exactly. Yeah, they famously, like Alvin Weinberg, I think he said this first for the homogeneous reactor experiment, which was one of these. He called it like a pot, a pipe, and something else. It's just a pot and a pipe basically, and a heat exchanger. So it's very simple. Like it's just a vessel with no intricate fuel assemblies or anything like that. But yes, the downside is that there's fission products, instead of being contained in little pellets with cladding, they're sort of everywhere in the system, and they're by the pump, they're by the heat exchanger and everything. So there's a lot of trade-offs sort of associated with that basic principle. Well, so for molten salts, which is another type of fluid, unlike water, it's, if you take table salt and heat it up, it will eventually turn to a liquid. And there are types of salts that can absorb and dissolve uranium at significant quantities and can be used as a fluid fuel for a nuclear reactor. And this was really first developed for nuclear-powered flight for the Air Force, which sounds crazy, but was an absolutely huge program back in the 50s. Started in the 40s, went all through 1950. We spent about $1 billion, $1950 over 10 years developing nuclear-powered airplanes. We never flew a nuclear-powered airplane, but we did a ton of work on them, and there were just huge, incredible facilities with all sorts of different options being tested. Very interesting technology development. Well, so the Oak Ridge folks thought, okay, we need a high power density compact reactor that's going to be able to make enough, if air comes in, it's got to heat the air up enough to like shoot it out a jet and fly a supersonic nuclear powered bomber. This was before intercontinental ballistic missiles. So this was like a Cold War, early Cold War type of weapon system. So they were like, well, they planned this reactor that was going to be a sodium-cooled, like a liquid metal sodium-cooled reactor with solid uranium oxide fuel. That was the original plan. And beryllium oxide moderator blocks. So it's kind of like the Seawolf reactor in submarine space. But as they started working on this at the really high temperatures and high power densities, they quickly realized that there was an issue with like a positive reactivity coefficient. The reactor was going to be unstable because of a temperature effect of xenon, which is a big neutron absorber. So xenon and solid fuel at those temperatures and power densities was going to cause the reactor to just be unstable. And they would have to have a very kind of fast acting and precise automatic control system to keep that reactor from running away effectively. And they were like, okay, that probably isn't going to work. So they then thought, well, let's go to fluid fuel. And let's use a molten salt, which they had done some chemical testing on before. And so the original change was like, just take out the solid fuel, take out the uranium oxide pins and put in closed tubes of molten salt fuel, stagnant fluid molten salt fuel. So like it wasn't flowing. It was just a tube. Like imagine a pin with some liquid fuel poured into it and then sealed off. This is like, we'll talk about all the startups later, but this is kind of like what Moltex, says. I think they say they invented this, but it was the original design of the aircraft reactor experiment. And so that solved the problem with the reactivity because it wasn't all the way full. And so if power temperature went up, the fluid would thermally expand and that would reduce reactivity enough to get around the xenon problem. Well, then they ran into some problems with that where there was a massive temperature gradient between the centerline temperature of that fluid and the wall temperature, to the point that the centerline temperature was basically at the boiling point of molten salt, which is like really high. So they decided, okay. Oh, and then there was one other problem, which was if you load up to start a reactor, like if you pour in molten salt at room temperature and then bring the whole thing up to high temperature, there's a massive reactivity change. And in order to do that, you would have to have like a huge control rod that you like pull out, a very strong, very neutron absorbing control rod that would be a control set of control rods that would just be pretty challenging operationally to go from sort of room temperature up to operational temperature and deal with the reactivity change. So they went to circulating fuel. And so they invented the circulating fuel, fluid fuel reactor. And they still are in this sort of these hexagons of moderator block, and the fluid goes in these tubes that are like serpentine. It goes up and down and up and down. They kept the sodium coolant, so there's still sodium coolant going through the moderator blocks, but also the fuel is also kind of acting as the coolant because it goes into a helium heat exchanger, so it transfers from salt to helium to water. And so it was like a real kind of Rube Goldberg type of thing, but again, very challenging, super advanced constraints. Like to make a reactor that can fly an airplane is like crazy, and they did crazy things to get that level of performance. So anyway, the thing, they finally got it turned on. It had lots of problems with it, sodium problems, salt problems, you name it. There were a lot of clogs, and as they were putting the fuel in, the tubes kept plugging, and just all sorts of problems. And then they wanted it to run for about 1,000 hours at full power, which would have been 3 megawatts thermal. But they ended up getting about, 96 megawatt hours out of it. So like 30 full power hours instead of 1,000. But it's still, they learned a lot. They got through a lot of the tests. There was one, they had to cut it short partially because at one point all the radiation alarms started going off, and it was found that there was a leak in some of the tubes in one of the cells in the basement. And then there was a leak in the cell through an electrical panel that was releasing fission products into the basement, like into the inhabited room. And so they did a couple things. The main thing they did was they put in big compressors and fans, and they ran a pipeline, like a 2-inch pipe, 1,000 feet to the south, and they just pumped the fission product gases into the forest to the south. And they also had to pull the radiation monitors like farther away from the reactor so they'd stop alarming and shutting the system down. So anyway, it ran about 4 days, and they got what they needed to know, and they shut it down. But it was kind of, exciting, but they did learn a lot. So that's aircraft reactor experiment. I'll stop there.
No, it's fascinating, right? Because we talked a little bit in our micro reactor episode about the Army nuclear reactor development project, and again, Camp Century, the nuclear reactor that was deployed in Greenland under the ice sheet for a base up there in Antarctica, an Air Force base in Wyoming. And it seems like every branch of the military was fascinated by the potential capabilities of nuclear. Obviously, in the Navy, that worked out really well for them. With nuclear propulsion, submarines, and aircraft carriers. But Army's working on sort of land-based systems, and then the Air Force, again, as you mentioned before, the intercontinental ballistic missile. The only way to, I guess, credibly deliver nuclear bombs at the time was in airplanes. Didn't have, ICBMs or submarine launches or those sorts of things. So, we have the Avro Arrow up here in Canada, which was, the world's best fighter interceptor jet, which was canceled. And there's a big sort of national mythology in Canada that it's because, we had a better jet than the Americans and you guys forced us to cancel our program. It was more likely that, ICBM sort of made fighter jets as kind of interceptors, not such a strategic it's not basically just made it obsolete. But in any case, this was motivating this drive initially. And it sounds like there's a lot of complexity in the reactor itself that probably made this not viable, but also just strategically, there was a revolution of technology and you didn't need to have bombers in the air for months at a time. I guess that was the idea, right?
Yeah. They would be up there for like at least, multiple days or maybe months at a time. Sometimes some of the concepts had like little fighters attached to the bomber that could like detach and go scramble and fight off people and then reattach. So that like, and one of the big motivations for it was you wouldn't have to have a bunch of bases in other countries in order to make it to the Soviet Union. So like you could just have like one big base or 2 bases in the United States, and those planes could just totally service the whole planet. And from those, so there was a lot of, it was thought that even though the planes themselves would, they knew they'd be more expensive to operate, but by not having to maintain bases in like foreign countries all around the world, the total cost was supposed to be cheaper, which is kind of interesting. And I should say, like,
this could be like an aircraft carrier model.
Yeah,
like,
exactly. Yeah.
It sounds like something you'd see in Star Wars, honestly, right?
There's a lot of Star Wars and Star Trek related things. I did get a really cool film digitized just, I don't know, a month ago. It's called the like 1958 Progress Report for Aircraft Nuclear Project. And it is awesome. It's like, it was declassified in 1980, maybe. It got more views than anything I've ever posted on YouTube, but it has, like, it summarizes the whole project, and there's some scenes and concept drawings, and all the comments on YouTube were like, that's the, now I can't remember which thing it was from Star Trek. They're like, that's exactly that shit. Like, everybody was saying, like, that's obviously the inspiration for Star Trek. So, and this fluid fuel reactor was like a pretty small overall part of the full project. There was a whole other reactor development program, which was using solid fuel, run by GE, and that instead of Pratt and Whitney, the fluid fuel stuff was Pratt and Whitney, solid fuel is GE, and those are the reactors out at EBR-1. There's these two big, funny-looking reactors with jet engines hanging out the back of them in the parking lot at EBR-1, and those are not fluid fuel, and they were like the thing that got a lot more money and a lot more development and testing in that program. So kind of the fluid fuel like went through this ARE, and then kind of got. They were like, yeah, we'll do this later when we need supersonic. But they reduced the requirements. They didn't even want supersonic in the end because it was too hard.
Well, yeah, this is what doesn't. I mean, I'm not not an engineer of any stripe, but certainly not aerospace. But the idea of nuclear rocket propulsion makes a bit more sense, heating up hydrogen and expelling that gas, right? But a nuclear powered jet, like with I guess molten salt reactors were looked at because they could get outlet temperatures of like 850 C or something. But if you think about when you combust kerosene in a jet engine, you're getting into the almost 2000s, maybe above. Like, could a nuclear jet engine actually go fast? Like, it seems like such a
after this. So there was the film I got digitized was part 1 of 2. The second part is still classified to this day, and it was about something called Project Pluto, which is when they took that technology even farther and developed nuclear scramjet cruise missiles, which went crazy fast and were fully nuclear powered, and they did a lot of like ground testing. This evolved eventually into like Project Rover and the NERVA, the nuclear powered rocket stuff. But that was originally all developed for a nuclear powered cruise missile in the atmosphere that went super damn fast. And like, yes, you can definitely maybe kerosene gets hotter, but you can't take as much, and like you can get a pretty high temperature nuclear reactor going and transfer a lot of heat to a lot of air, forever. And so, you can there's still like material challenges and radiation issues and all sorts of stuff. But like conceptually, you can make a very high performance jet or cruise missile with a nuclear reactor.
Crazy.
Yeah, it's crazy. It's a bit crazy.
Okay. And just, I guess, like last thing in terms of, other things that contributed to killing that program, like how would you shield a reactor on an airplane like that from the crew? Was that like, were these other things that just didn't kind of stand out, or it was like,
no,
someone else's problem?
They did a ton of work on it, and all the really early shielding work, fancy shielding work was done for this problem. They even lifted reactors up on these huge towers in Oak Ridge, the tower shielding facility. Massive amounts of money were spent on shielding. And the idea was basically directional shielding, because you can't carry 100-ton shield like you would normally need around a reactor like that. So what they did is they made like shadow shields where like they shielded the crew were like, the reactor's back here and the crew's way up here. And they put the crew in this like really thick leaded little crew cabin. And then they put numerous like other shields just between the reactor and the crew cabin without shielding the stuff, going out the other side. So basically this reactor would just be absolutely shooting out radiation in all directions. And they just tried to shield the like one direction that the radiation would have to go through to get to the crew. And the crew was still getting pretty big dose, even though there's a big plane, but you would still get pretty significant dose. And we did actually we took one reactor called the Aster, the aircraft shield test reactor, and we put it on a plane, a modified, what was it? Anyway, a giant Convair bomber plane. We put it on a plane, we turned it on, and we flew it around. Like those guys were up there. We flew it like 42 times, and there were these, planes following and taking radiation measurements all around. And the crew cabin had So we did all sorts of like actual in-flight testing of operating still smaller than you need, but like a couple megawatt type reactors. So yeah, the shielding is like a major problem in the air.
All right. Well, nukes in airplanes, snakes on planes. Let's park that for a while. But I was super curious. We had to go a little bit into that to set the scene for this development program, and it is serpentine as you're mentioning, but it ends up at Oak Ridge's National Lab. I guess that's where the initial aircraft reactor experiment was, and it evolves into the molten salt reactor experiment. What's the impetus there? Are they trying to make commercial nuclear power? Is that the vision for this?
So like Alvin Weinberg, who is the director of the lab and was one of the OG, Manhattan Project founders of the industry of nuclear power, he really wanted to make commercial nuclear power. He was like super into that. And he wanted to find a way to make economical power with nuclear reactors. And he really liked the idea of fluid fuel in general. He really pushed on that homogeneous reactor experiment, the aqueous homogeneous one. And he eventually was like, understood that wasn't a great option. But after they had this molten salt option, he was like, this is what we need. Now we can use molten salt to make a power reactor for commercial electricity, and there's plenty of reason to think it will be, cheap and stable and all that kind of stuff. And so let's build a reactor experiment, a medium-sized prototype with all, most of the systems in place to prove out that it would work, and then that would form the basis for building like a more full-size prototype or demonstration reactor. And that was kind of the birth of the molten salt reactor experiment. We'll dive right in, but just one more thing. There was a second molten salt reactor that operated as part of the aircraft program called PWAR-1. It was the mock-up for like the thing that was supposed to come after ARE, which never really happened. But it's like a fun little side note that we ran. We've actually run 3 molten salt reactors in this country. So ARE, PWAR-1 mock-up, and MSRE. But anyway, that's just a footnote. So let's see, Weinberg, and by the way, Weinberg told JFK that he didn't think the airplane reactor thing was going to work. That was another reason he got shut down. He got in big trouble because all his friends, worked at the aircraft. Everyone was getting paid by the aircraft program. And he was like, I just don't think it's feasible. And Kennedy shut it down as one of his first things he ever did in his administration. And anyway, so I think Weinberg wanted to say like, hey guys, we can continue this research for something that actually makes sense by making the MSRE. So yeah, he hired a guy named McPherson in like 1958 and put a group together. No, 1956. And McPherson took the design lead for the molten salt reactor experiment. They chose a salt based on what they had learned from the previous molten salt work on the airplane program. The salt they chose, like if you take uranium UF4, that's a salt and it absorbs or it dissolves enough uranium. It's a fluoride salt, but it has a really high melting temperature. So then they were like, okay, let's add in beryllium F2, DEF2, and that's going to bring the melting temperature way down. So now you can contain uranium, you have a good melting temperature, but it was too viscous. You couldn't pump it, so they had to add something else. So they added lithium fluoride LiF. And so now you've got FLiBe, so it's fluorine, lithium, beryllium, and uranium. And that's the salt that people are still excited about today, at least most people. There's other options as well, but that sort of ternary salt has sort of been the foundation of molten salt reactor salt choices for those kind of 3 reasons. So they chose that salt. They did all sorts of chemical studies and so on. And then they began constructing the molten salt reactor experiment at Oak Ridge in 1962. It took them like 4 years. They went online in 1966. And by the way, they used the building that had been built for the aircraft reactor test, which was like supposed to be the next thing, got canceled. So they were like, well, we'll just throw the MSRE in there, which later was thought to be a bad move because they kind of backfitted a different project into a building that wasn't really made for it. Anyway, and like overall, the MSRE ran pretty well. Like they had problems with it. There's lots of lessons learned. There's like great the documentation is extreme. There's just thousands of pages, thousands of documents with all the operational details of the MSRE. It had some major milestones. It ran, there's like a great picture of Weinberg riding 10,000 hours. They got like their 10,000 full power hours out of that thing without too much trouble. Like the reactor itself ran well, but the Some auxiliary equipment was a pain. Like there's this thing called the enricher sampler, which is like a whole system where you would put more enriched uranium in and you would pull salt out to take samples to see what's going on in the salt to measure the corrosion products and the oxidation state and whatever else. That thing was a huge pain in the ass and like really caused a lot of trouble. Just you got to keep moisture out and it's super radioactive. And anyway, that needs more work.
Do you feel like conceptually, like I'm just trying to get my head around this as a non-engineer, as a non-specialist, and trying to find sort of some simplifying analogies. I think, again, it can't be stressed enough that whereas in a conventional nuclear reactor, this alchemy, this kind of creation of, half of the periodic table through radioactive decay and transmutations and neutron absorption is happening sort of within a contained fuel assembly, within a pellet. There's gases that are being formed, but they're being contained more or less, right? We have very few kind of fuel failures, whereas this fuel is by design liquid. This alchemy is occurring within a larger containment, but it's flowing out of the reactor core through your heat transfer, your heat exchange mechanism, et cetera, just kind of freely around. And that's some really, really complex chemistry. So it sounds like you have a reactor, but you have a chemistry plant, which is an essential part of the process. So I'm just thematically, first principles, trying to get a sense of trying to explain this and make it understandable.
Yeah, sorry, we should definitely hit some of the high level stuff. Yeah, I mean, it's a fundamentally different idea. It's like instead of having that first two barriers where you have like the fuel pin and the cladding around it, you're sort of saying like, forget about it, just have the whole thing be in all the primary systems. As you said, the pipes, the vessel, the pumps, the heat exchanger, all the instrumentation are now sort of have this extremely radioactive, all the fission products, all the actinides, all the fuel, everything. And it even goes, as you said, outside the core through the heat exchanger back in with all the fission products and fuel and everything. So there's like fissions happening in the heat exchanger, right? Because some of those fission products are delayed neutron precursors. And so the neutrons come shooting out a little bit later. So they flow out of the core. And like off in the heat exchanger, they may shoot out a neutron and then that causes a fission. So your heat exchanger has to be ready for fission. But there are some real interesting reasons why this, is kind of exciting and interesting. I mean, one thing you can do with a fluid fuel system is like you can constantly be processing chemically that fluid as it's going by, and you can pull out certain fission products just on the fly. So in a solid pin reactor, you might be building up fission product gases that are strong neutron absorbers. But in a fluid fuel reactor, well, you can be bubbling through some gas and just pull those fission products out all the time. And so you can really this helps you run the reactor for longer. You can obviously keep it running. You don't have to do like a shutdown. You can do online refueling. You put some uranium in over here and it is automatically in the whole system. There's no like structural steel or zirconium around it. And so you have you can improve the overall neutronics because you're not wasting neutrons in sort of extra materials like that. Yeah, and you don't have to fabricate the fuel. Like you don't have to, I think Karush was saying he was talking about like a light water assembly has this like Swiss watch type mixers and vanes in each fuel assembly that you have to fabricate. And it costs not a big fraction of the money, but it costs some money. And so with this type of fuel, well, you have to synthesize it chemically, but you can do that in batch and it should be cheaper to like make the fuel. You also can go to much higher temperatures. So you get all the advantages of high temperature, better thermal efficiency. Maybe you can do process heat. You also get the disadvantages of high temperature, which is that you have more corrosion and your materials have to be more expensive and fancier to be able to maintain their integrity at high temperature. So that's a pro and a con. It's low pressure in general, not super low pressure. I mean, you may still have a few hundred PSI, but it's a lot less pressure than like a pressurized water reactor. So you don't need the super thick pipes and vessels and all and emergency core cooling, high pressure injection systems. And so there's safety advantages associated with that. So you can get all the safety advantages that we talk about for most Gen 4 type reactors, where it doesn't necessarily need like a diesel generator to passively cool and transfer its decay heat out in any kind of accident scenario. So lots of advantages, but yeah. Oh, and it's really good at utilizing thorium. That's another thing that Weinberg was really interested in. it's because it's fluid fuel and because you can process it on the fly, it works well with a thorium breeder reactor concept. Thorium, you may remember, can be a breeder reactor, but only if you slow the neutrons down. Well, it works best if you slow the neutrons down. Like thorium's unique capability is that it can breed with slow neutrons. Plutonium breeders need fast neutrons. Thorium can kind of do either, but it's like best at with slow neutrons, which has some advantages. Like you don't need like HALEU to start up a thorium breeder, which is cool. You do need HALEU to start up a plutonium based breeder. So like there's this idea that you could start up with like a pretty small amount of fuel and then you could breed through thorium to get long-term breeder type sustainability, world scale sustainability forever. And like that's a pretty good story. So that's a good long-term commercially viable potential story for like nuclear for electricity. So that's kind of what they were thinking. The reason the fluid fuel works well with thorium is that when thorium first absorbs a neutron, it becomes protactinium-233, which is a strong neutron absorber. And so you really want to get that stuff like out of the core so it doesn't gobble up the neutrons for 27 days until it decays to uranium-233. Then you bring it back and it's the fuel. And so in fluid fuel, it's like you can kind of pull that protactinium out on the fly because you're constantly processing things, and that makes it really work well. Whereas if you had solid fuel, it would build that protactinium up and it would stay right there. It would gobble up a bunch of extra neutrons, and you could make it happen. Rickover sort of proved that with the light water breeder reactor program in Shippingport, but it's much better, more elegant in a fluid fuel molten salt breeder reactor. So that's the like overall spiel for like what they were trying to do and why they thought it was going to be a good idea.
Yeah, it strikes me that there's like so much experimentation occurring at this time and like a decent amount of budget. Like you mentioned, $1 billion, like 1950s dollars or 1960s dollars that went into this. Was part of the rationale perceptions of uranium scarcity?
Yeah, that was definitely in mind. Like, again, I think I've said it a bunch of times on here, but like there really was this thought that like, the thing that matters for commercially viable nuclear power is breeding. Like it sounds dumb now because breeder reactors have always been more expensive overall than non-breeders, but they really thought, and it's probably still true, like especially for long-term, large-scale operation of nuclear, you do need breeder reactors because at some point that uranium is going to run low, like the mines are going to get depleted a little bit, and like the reactor that can make economical usage of trace uranium or thorium, thorium in granite, thorium or uranium in seawater, is obviously going to be the long-term economical one. They weren't as concerned about like capital cost. So that's kind of shifted. Like as we keep finding more and more uranium and as capital cost is like higher and higher fraction of the cost of nuclear, like the breeder idea has sort of fallen out of interest. Like we aren't focused on needing breeders to be economical, but we only make 5% of world primary energy from nuclear. If you make 50%, like you're going to be wanting breeders pretty fast. So it's still true that we want breeders and we need them for economic reasons, but it's like on hold. It's like delayed. We need to first be able to scale up the nuclear fleet cheaply and economically and compete with other sources before we even demand that much from uranium. Like every time you go looking for uranium, we find more. So yeah, I think we'll need them, but it's like been delayed to like 2050 or whatever. Assuming we build triple nuclear now, then you're going to want breeders like pretty quick.
Right. That's a big assumption, but a guy can hope. So I think most people can get their heads around this idea of, having I'm not even sure if you call it a reactor pressure vessel anymore because it's not under substantial pressure, but having a reactor vessel where the salts are fissioning because there's a moderator there, some graphite, I think in this case, and then this molten salt circulating through a system, exchanging heat, etc. I think what's harder to sort of visualize is the whole chemical plant side of a molten salt reactor. And you mentioned, a couple of processes, bubbling off some of these neutron poisons like xenon, extracting protactinium-233. What did that look like in the actual molten salt reactor experiment building? I'm imagining hot cells, like, just in terms of isotopic separation. I know that, a huge part of the Manhattan Project was just figuring out the instrumentation to do that. But how hard was it to do that side of the project? Was that like 30-40% of the effort of running the thing was just managing the chemistries, or?
Yeah, I'd say it probably was like 30-40% roughly. That's a good ballpark. And there are like pretty cool diagrams you can see. Like, again, there's like infinity documentation. I should send you some links that people can kind of look at the layout of the equipment and so on. In MSRE, they were not a full-on thorium breeder. So they ran originally on just U-235, like enriched uranium. And they did eventually switch over to uranium-233. They swapped one uranium, but they never did like a full like thorium blanket thing with the protactinium separation. That was not actually operated in MSRE. But they still had lots of, again, this enricher sampler thing was like a big thing. And there's like the reactor, and then there's a bunch of tanks. There's dump tanks, there's purge tanks, there's flush salt tanks that you can like clean and decontaminate equipment out with. There's all sorts of little ports that you can hook up to and like get some gas out. There's something called cover gas. So like above the fluid reactor, there's like a cover gas with some pressure on it, and a bunch of the volatile fission products go up into there. And so there's constant like cleaning up and filtering of that cover gas. And like some lessons they learned were like, well, we need a lot more metallic fibrous filters on any of the gas lines coming out of there, because they kept getting metallic fission gas vapors that came out of those tubes. So these are like a lot of interesting and important lessons learned. But yes, it's like, well, the reactor itself, it did have channels of graphite, like big stacks of solid graphite, and the fluid fuel flowed through that. But other than that, it was like a pretty simple internal structure for a reactor with lots of chemical equipment on the outside. It's been like these reactors are much more chemical reactors than nuclear reactors in a sense. But I mean, the chemistry isn't like, yes, you get 50% of the periodic table in there, but the way these salts work, like a lot of those fission products are soluble in this salt and just kind of chill in the salt. And like, yeah, there's a question of like, what's the waste product look like? Like, how do you deal with this huge volume of salt that has all these fission products in it? Like, what's the long-term nuclear waste solution? But like during operation, most of them just didn't cause too much trouble. There are issues of a few of them. There were like snow traps. Like you can get fission products, vapor snows that can cause or fogs or smokes, and those things can block heat removal pathways. And so that's something even today people like spend a lot of time trying to figure out in an accident condition, how much snow are you going to get from your various volatile fission products, and like, is that going to block the heat removal pathway or coat out on some of the cold surfaces and prevent heat transfer and then overheat the vessel so it fails? Like those are like the safety concerns and situations now. So there is a lot of stuff to deal with, all that stuff. And yeah, it's totally it's operated all behind massive shielding, fully remote. And that's like one major operational challenge in a pressurized water reactor. If a pump breaks, you can like turn off the reactor. The induced radiation in the water goes away after like 7 seconds, and you can walk in there and do some maintenance on the pump. You can pull the pump motor, you can fix a wire, you can adjust the thermocouple, and you can walk back out and turn that reactor on. Can't do that in a molten salt reactor. The pump is so radioactive, like it's absurdly radioactive. Like I don't think people understand the like 8 orders of magnitude of radiation that are around and operating a reactor that has fission products. Even after you shut it down, you can't go anywhere near it because, again, all the fission products are in there decaying away. So all the maintenance was done remotely, like with robots and manipulators on like cool, like cranes that would move around, and they could do crazy maintenance. They could like go in there and like chop a tube and weld it. Like they were doing all sorts of like pretty intricate maintenance. If there's a great YouTube video, I did not digitize, it's been up there for a long time, that shows like, I think it's called like remote maintenance of the molten salt reactor experiment or something like that. And they should, and one of the lessons learned was like, if you're going to put bolts in the reactor cell, only have like one bolt head size, because it was a pain to like change out socket wrenches to different sizes for the different bolts they were trying to do remotely. If you drop something, it's hard to go find. So anyway, the overall maintenance and repair is like a whole new world for this type of reactor. And again, they showed it can be done, and they got it done in the mid 60s, mid to late. And like, It's not problem free. Lots of lessons learned. It is a big challenge. It probably has lots of operational costs. There's probably a lot more radiation leaked from that kind of system, probably at low levels than something where the fuel itself is like deep within the fuel pin. But so anyway, it's not a showstopper, like for sure. It's definitely not. It's hard. It's a trade-off, but it's not. It doesn't kill the program.
Conceptually, if you go from a pressurized water reactor where there's a secondary loop and your primary loop has some contamination in it, but everything's kind of contained there, to a boiling water reactor where now your turbine needs shielding, but again you turn it off and that those products decay away very quickly and you can get in there and maintain it. The molten salt reactor is on a whole other sort of level in terms of contaminating, as you said, the pumps, I guess the heat exchangers as well. One thing I heard about, and I'm trying to draw some analogies here with the high temperature gas reactor experience. When you have high outlet temperatures, I understand the steam generators are a little trickier because that's where you're going to have your big sort of deltas in terms of temperatures, one side to the other, more opportunities for stressing metals and things like that. This reactor, there was no power conversion system. They were just shedding heat, I think, to air. Is that correct?
Yes. They had a giant radiator.
What are the potential issues beyond just those higher temperatures with electroplating of noble metals, I think I was reading about?
What you said already kind of like does cover a lot. There were a lot of lessons learned and like worrisome things about like thermal stresses, like just they put electric heaters all around these systems because you have to melt the salt to make it liquid, and when it melts, it goes through a phase change that expands dramatically. You can rupture a tube easily going through a phase change during heat up, and you can also induce very strong thermal stresses if you do it wrong. Like if you're not heating it up uniformly, you can cause a thermal stress that will snap something or break a flange or cause a leak or whatever. So a lot of the lessons learned from MSRE were like, make more heater controllers and control them with computers. They were like really into computers at this time. They're like, computers will solve this. And they had a pretty fancy computer at MSRE, but they were like, depend on it more, have it like heat up the whole system in a way with many more degrees of freedom so that it very evenly heats things up without inducing these massive thermal stresses. That was one thing about operating at those kind of temperatures. And then like inside the vessel, you're right, like there is complex chemistry where when you have 50% of the periodic table, the solubility of all those thousands of chemical compounds is temperature dependent. And so if you've got hot reactor core and there's a solubility of some fission product chemical, and then you go on out to the heat exchanger, and the heat exchanger is at much lower temperature because that's where you're transferring the heat out, then the solubility of that thing changes, and it may plate out right on the heat exchanger surface. It may plate out on the vessel walls. It may interact with the vessel walls and start causing like cracking of the structure. And so there are lots of things to worry about with just the inherent temperature gradients. You can't get rid of temperature gradients in a reactor. And so there's mass transport from across thermal gradients based on the super complex chemistry in there. So that's what most people like studying molten salt reactors today are like doing studies on. They're running flow loops, corrosion loops. They may put in non-radioactive fission product surrogates, so you can put in like a stable zirconium fluoride that would act chemically just like a radioactive zirconium fluoride, but doesn't have the challenges of the radiation. So a lot of work like that going on. But yeah, those are the key challenges of this. And then just in terms of once you go to the power conversion cycle, it's not really much different than any other high temperature heat transfer stuff. Like once you have high grade heat coming out a heat exchanger, yeah, it has to be made of metals that can handle it. But we have much higher performance, high temperature metals for a balance of plant. Once you're outside the radiation and chemical regime, it's kind of no big deal.
No big deal. Okay. Yeah. I mean, I was looking at this, I'm not sure if it was electroplating or what I was like, what the hell's a noble metal? I'm like, gold, platinum. This sounds like this could be a really valuable heat exchanger once you pull the thing out. But of course, it's going to be radioactively very hot. There'll be a few more things involved in the mix there. No, it makes me think a little bit about, the important work that's being done at a much lower sort of technology readiness level in terms of prototyping parts, doing salt loops. I think we're in a little, I think think it's a pretty constructive Twitter conversation with the CEO of Valor Atomics. They built a prototype and are doing some kind of thermal testing, non-radioactive testing of a mock-up reactor they've done, which is, it's awesome that they're doing that and building it.
It's cool.
But add in the fission and things get a little more complicated is sort of what the molten salt reactor experiment teaches us.
Yeah, that guy, Isaiah, right? He's passionate, right? And he's moving fast. He's like, I want to solve this problem as fast as possible. So they like pounded out this thermal prototype for a micro high temperature gas reactor in 18 months, it's cool. Like the video is totally cool and they're having fun with it and they're working hard. And yeah, I mean, my point was basically like, this is cool. I don't mean to like rain on their parade or anything, but yeah, the hard lessons are all with radiation. And so like but I think they get it. He's kind of agreed. He was like, yeah, we're trying to get to a radioactive, actually nuclear prototype as soon as possible. And one thing he can measure with that thing he built was the helium leak rate, which has been a problem in those kind of reactors. So I'm like, what's your helium leak rate? They're measuring, he's going to get back to me. So I'm excited to hear, how maybe it'll be bad at first, but they'll figure it out and fix it, and then they'll have it good once they do the actual radioactive one, which is where it matters because you don't want to leak your slightly radioactive coolant after some fuel cracks. But yeah, I think that was a fun conversation. I like engaging with those guys.
Yeah, no, I love it because it's always constructive, but I think you bring some good realism. Okay, so maybe let's shift gears a little bit to talk about the kind of cultural mystique, the meme that the molten salt reactor has occupied. Like, why is that? Let's walk through. We've sort of gone a bit into the kind of historical context. We've deep dived some of the technical issues. There's obviously way more than we can get into in a simple 1 hour episode. But now there's kind of this cultural element of it. So this is something you've been a bit of an anthropologist of, so
sort of. I'll give you
that.
my sense of it. And this is much less technical. But so from my perspective, I mean, first of all, so molten salt reactor shut down on their own free will. They were going to build a bigger one, the molten salt breeder reactor demonstration. But it got canceled by Milton Shaw, who wanted to put all the money from the Atomic Energy Commission into the Clinch River sodium-cooled fast breeder program. And so molten salt was canceled, in 1969 or whatever. And then nothing happened. They did some studies. Oh, sorry. Let me just mention one more thing on MSRE. They thought it was such a great idea. They put together a full program plan and published it in this document called ORNL 5018. That's like the program plan for molten salt breeder reactor. And it listed out everything. They were like, molten salt breeder reactors are great. Here's everything you need to do to commercialize the program. They laid out schedules, ASME, code cases needed for the vessel material and schedules and budgets. And it's just a beautiful, wonderful document. Anyone who wants to do a molten salt reactor, grab that document and just do whatever they say. So it goes on hold for a long time. In 2001, the molten salt reactor was chosen as one of the 6 Generation 4 reactor types that was promising for the future. So it became a Gen 4 reactor. Some work was done in Europe for years and years. And then Kirk Sorensen happened. And this is Kirk Sorensen is this, I think everyone probably knows who he is. He's this nice guy. I don't know if he's from Alabama, but he worked at NASA for years. And at one point he found a book from 1958 called Fluid Fuel Reactors. It's one of those Atoms for Peace books. And he was reading through it and it talks about all these reactors we're talking about, the aqueous homogeneous, ARE and MSRE. And he's like, this is amazing. This technology is awesome. It's mostly forgotten. He was seriously involved. I think he went and got a bunch of the old documents digitized from some library at Oak Ridge. And he dug up all this information. He got real excited about it. And he started making modern media, pitches for it. And he explained it in YouTube videos and whatever else was going on back then. This may have been in I guess 2011. No, it must have been before that. It was around 2010 or so. And I actually met him and Rod Adams and he and I were hanging out at an ANS conference somewhere around then. And we were talking about, nuclear blogs or whatever, which is what the social media in nuclear was at the time. It was the 3 of us. And I remember Kirk being yeah, first of all, thorium and molten salt are awesome, but also nuclear just needs a rebrand. We need to be able to say yeah, that's old nuclear, but check it out. There's this whole new thing and it's totally different. It's totally better. And so a lot of what I think he was trying to do he definitely believes in thorium molten salt reactors, but also he like really wanted to like give the world like an opportunity to be like, if there's something cool and new. And so he hit it from that approach. I think he wanted to rename, I can't remember. Anyway, um, so he hits YouTube and he spreads the sort of the gospel of thorium molten salt breeder reactors, and it is a hit. Young people are like convinced. They're like, this is it. There's a bunch of like myths that show up, like you can't make bombs from thorium, like, which isn't true. We can talk about myths if you want, but like there's this whole mythology around it that like shows up kind of based on his videos, and people just start absolutely spreading it, and it just goes absolutely viral like around the world, to the point, like I said at the beginning, that everyone's like, oh, you do nuclear, like tell me about thorium molten salt, like I saw this guy on YouTube, and it's all Kirk. He's like it's amazing what he's done, and it's not like, part of me was like, oh, everybody thinks all these myths are true about thorium, it's like a little bit overhyped, blah blah, but now I'm sort of more wise to it, because I know tons of people who didn't think about nuclear their whole lives. They heard about thorium basically from Kirk. They were like, that sounds interesting. And they went looking into nuclear, and then they were like, oh, nuclear in general is great. And I remember like people like Izzy, Isodope came through a thorium pathway and now is, saving Diablo Canyon with a group there. And, Eric Meyer from Generation Atomic got the thorium bug and was composing operas about thorium molten salt reactors, and now is running this big, like, industry-wide or worldwide nuclear advocacy group. And, like, so yeah, it's become this feeder for, like, young people or people who never thought about nuclear to, like, learn about nuclear. So it's not just about thorium, but it's... Anyway, so he's around. He, like, made a company, and he still is out there, talking about it. So I think he, like, single-handedly probably shifted like the whole narrative on nuclear in general for like a whole generation using like YouTube videos. And now there's like dozens of thorium molten salt companies and startups doing all sorts of stuff, raising big bucks and making cool facilities. And it's like all kind of off and running, to the point that there's like a few basically under construction right now for some prototypes.
So in terms of what made Kirk Sorensen's a charismatic guy. He's a great speaker. I think I tack myself alongside Izzy and Eric as having drunk the thorium Kool-Aid after, I think, Kirk holding up like a golf ball size metallic piece of thorium and going, wow, this could power my entire life. Wow, this is such a great environmental story. But there's more there. There's more ingredients there. There's sort of like some degree of sort of conspiracy theory around sort of why the program was canceled. It answers all of these questions and problems with nuclear, like proliferation and safety, and it must have been suppressed in some nefarious way.
Right. That's the
I guess.
Story. Yeah, so I guess yes. Maybe that stuff was like part of this overall recipe for making it go viral. Because there's a great book I read years ago called Made to Stick that kind of tells like what are the elements of storytelling that makes everybody remember. And and one of the examples it gives is like, everyone's heard the story where you wake up in a bathtub with ice and there's a note that says, call 911, like we stole your kidneys, right? Like everybody's heard this story, and it like breaks down like what about that story makes it so memorable and viral. And anyway, it's a good book, and I think the thorium story definitely has like a lot of elements, and it is these conspiratorial things where it's like a little unexpected, like, did you know that this little ball of thorium can power your whole life, forever? And it's like, no, I didn't know that. Tell me more. And then it's like, did you know that we stopped making thorium reactors because they just couldn't make bombs, and big uranium suppressed it because we needed to make more bombs during the Cold War. And like, had we just done thorium, we'd be a much more peaceful and prosperous world. And that's like, oh my God, there's been an injustice. Like, we must fight for thorium. Now, yeah, so I mean, that I think fires people up and gets people engaged. It's a much more interesting story. There was an underdog that was suppressed for military reasons, and like, it's what we need, and like, it's so much better. You can't melt it because it's already melted, which that's such a nonsensical, like, it's already melted is like you're already halfway through an accident sequence. Like, it's not a good thing. But anyway, yeah, so it has elements of those things, and I did end up in like 2014, I wrote a page on what is nuclear called Thorium Myths. And I broke down the myths in some detail with citations like, this thing about thorium being shut down because you couldn't make bombs. It's nonsensical. It doesn't make any sense at all, because like in the Cold War, we had plutonium production reactors. There were graphite moderated natural uranium fueled reactors at Hanford and heavy water moderated reactors at Savannah River. They were like very specialized plutonium production reactors, and we made untold amounts of plutonium, way more than we needed. In fact, the commercial nuclear industry was like, in its early days, was like, oh, we could sell plutonium, to you guys, and that would help our economics. And the government was like, nah, we have too much. We aren't paying you guys for your plutonium. Plus, light water reactors don't even make good plutonium. Like they make poor isotopic quality. So the idea that like light water reactors are somehow planned to be used to make plutonium it never was the case. It's totally nonsensical, but everybody says it. Like every single Reddit comment every single day about thorium, someone comes in there and says, we shut down thorium because you couldn't make bombs. That's wrong. We put thorium in Indian Point Core 1, and it's right there in the conference proceedings. They didn't have it in Core 2 because it was too expensive. It was cheaper to use lower enriched uranium and no thorium. It was purely economical. And like the same kind of thing happened for the light water breeder at Shippingport. So like all the myths are basically wrong. Like I have like 7 myths, and and the idea that you can't make bombs from thorium is also hilariously untrue. There's a great letter that I found that is from America's top nuclear weapons scientist from Livermore. And they did an analysis of the weapons usability of uranium-233 derived from thorium. And they have this great line in there. It's a short letter. And they're like, we evaluated U-233, and it's a great bomb material. And the statement was made that if all of our nuclear weapons today were based on uranium-233, we would have no interest in switching them over to plutonium, meaning there's nothing about plutonium that makes a better weapon system. We're just going to keep plutonium because that's kind of what we have. But if it just happened to be U-233, there would be zero technical interest of any kind to switch to plutonium. So that tells you how good it is as a weapons material. And the thorium people they've yelled at me and thrown huge emails at me, and like, I say, oh, you'll put in, you'll dope it with a bunch of U-232. It's like, okay, that may help if someone breaks into your reactor and tries to steal weapons material. Sure. But the real concern isn't that. It's that if you're or whoever, and you are running a molten salt breeder reactor, you can go in there and you can dip in a very simple chemical cell, pull that protactinium out right as it's generated, and have it decay outside the core. It will decay to pure weapons grade uranium-233, like no doubt about it. And so those reactors need safeguards and inspections just like any other reactor. So there's no, like, it doesn't get around proliferation concerns. They need just the same, maybe more inspections and safeguards than any other reactor. So again, these things are not said. Like, I kind of fought back against it and got people mad at me, but I don't know. It's part of me is like, maybe it's not worth fighting because so many people are getting excited about nuclear, but I don't want people to have like false expectations. Like if we go out and build a bunch of thorium reactors and then someone says, hey, these guys just broke out and became a weapons state. Like, I thought that was impossible. I don't want that to be a surprise. So the engineer in me is like, let's keep it realistic. There are benefits, there's pros and cons, but like, let's not say stuff that's just straight up not justifiable.
Mm-hmm, mm-hmm. So you mentioned, an enormous amount of excitement has been generated. There's a whole number of Western startups, but in China, there's actually a operating thorium-fueled molten salt reactor, I believe.
Yeah, well, yes, probably. It's hard to find like these. They've kind of gone a little bit quiet, but yeah, I mean, this is a crazy story. So it was back in like 2016 or something. The Chinese Academy of Science started a huge project, 500 people, hundreds of millions of dollars, to build some molten salt reactors. Their plan originally was to build 2 prototypes. One would be a molten salt cooled reactor with solid fuel called a FHR, similar to what Kairos is building.
Kairos, yeah.
And then the other one was going to be a 2 megawatt thermal molten salt reactor, very similar to the MSRE, but with actual thorium in it. They were going to be the first one to like actually put thorium in it and do the breeding and everything. So they went off and they built the thing. I mean, there's a guy who's on Blue Sky now named Conrad K. I don't know how to say his last name. Knopfer. Anyway, he's been tracking like publications for years. It kind of stopped in 2022, but he found photos, detailed publications, newspaper clippings of that thing under construction, the like full-on molten salt reactor. And you can see it, like, sure enough, he's got satellite photos of the progress, and it was completed 100%. And around 2022, they went off, they trained operators to operate it. They got authorization from the regulator to turn it on. And then it kind of like news kind of went dark, and this may be for like U.S.-China relation reasons or something, but it became a little bit harder to get like the latest and greatest information. I have heard conflicting reports that like, yep, they went to full power last year. It's up and running. And like they're taking the next steps now. I've also heard that like it's gonna reach full power soon. Like I don't have the high res information. I'm sure somebody who can like go in there and maybe read Mandarin news or something could find out a little bit more info. But I've been kind of telling people that like we're gonna see headlines that are like China turns on thorium molten salt reactor, and like that's real. When I was telling people a couple of years about it, they're like, "Oh, that's not real. I don't even believe it's happening." And I'm like, "Look at these photos that this guy found," and like they're like, "Whoa, damn! Like that's that's real equipment. They're really doing it." So yeah, that by far is, I mean, it's basically, they're picking up where MSRE stopped. They've rebuilt it completely. They probably added their own innovations and new, modern technology. And like, it's either on now or it's going to be on soon. And that'll for sure be the next molten salt reactor, if it isn't already, that's online. So that's definitely the biggest and most exciting thing going on in molten salt reactors on the planet that I know of.
Right. No, and I mean, it's so telling, right? I mean, it's 500 people, hundreds of millions of dollars invested. You mentioned this publication, ORNL. There were some numbers that came after it.
5018, yes.
Yes, forgive me for not remembering.
Yeah,
I should commit that to memory. But, I think it did talk about sort of what the timelines and investment cycle would be like, because I think there's a lot of startups saying, hey, for another 10 or $50 million, we'll be commercially operating something in a little while. What did that document claim in terms of giving us a sense of the path forward?
It was for like, if I recall, it was something like 10 or 12 years and 10 billion modern dollars is roughly what they were talking about. It was a pretty big program, and that involved getting the code cases again for those structural materials, which takes a long time, and also really formally developing the protactinium separation technology with the breeding and getting the blankets and other reactivity coefficients figured out. So there was quite a bit of technology development for a full-on molten salt breeder. And I will say a lot of the like startups right now are kind of saying like, yeah, we think we can make, everyone has a render of their like little tiny reactors, and there's thousands of them on a ship or in a shipyard or whatever. But like, and they say, everyone says they're going to be the cheapest thing ever. Of course, that's just tradition to say. You don't really know how much you cost until you're up and running with a nuclear prototype. So might as well not really say what you cost until you've got that prototype up and running. Like the nuclear prototype, it should be a rule. No cost until you're splitting atoms. But yeah, a lot of them are working on like just steps in the direction. So like a lot of people have already run non-nuclear molten salt prototypes, and they've learned all sorts of interesting and important things about plumbing molten salt, operating with molten salt before you have to deal with the radiation. And that's good. We're sort of rebuilding that knowledge. There's a couple like actually nuclear small prototypes that aren't intending to be what that document said, which is like build a full-scale commercial breeder reactor. A lot of the like ongoing efforts are just sort of like, let's make a non-breeder and just learn something from it, like a research reactor or a prototype. So far, like there just aren't too many people who are planning, or at least publishing detailed plans that are much different than like a 12-year plan to like commercial. I think that's like kind of in line with what most of them are thinking.
Is there a way, because it sounds like one of the biggest complicating factors here is that you have a massive chemicals plant as a part of this. Is there a way to minimize that side of the project, and maybe, and I've heard a lot of startup ideas are around having a core that doesn't last very long at all, right?
Yeah,
and
totally.
Swapping that in and out. Are those efforts to kind of reduce the complexity of the chemicals challenge?
Yeah, that can definitely help. If you don't have to worry as much about corrosion or erosion, or if you're getting 50 ppm of like whatever corrosion product coming in per day, like they had at aircraft reactor experiment. You can avoid solving that problem by just saying like, oh, we're just going to throw away our vessel every 4 years or whatever. And so, sure, okay, but and they use cheaper materials. Like you can use stainless steel 316 instead of Hastelloy N. And like if you throw it away every once in a while, like every couple years, then okay, there may be a case to be made there. You will be generating, a waste stream of like stupidly radioactive, highly activated and contaminated. There's going to be like a bunch of cobalt 60 in there from the neutron activation. So you're making this like whole waste stream of like the people who show pictures of like wind turbines, in the dump. Now just imagine a bunch of like super radioactive reactor vessels every couple, if you build thousands of reactors, you're going to have just tens of thousands of these like radioactive. It's kind of a mid-level waste, but it's pretty hot stuff. So I don't know, like, is that gonna scale? Maybe not, but maybe it's an okay way to get started with the first couple while you're developing a fancier, higher endurance Hastelloy, a cheaper version of a structure that can actually withstand that chemical environment for that long. So yeah, that's kind of what a lot of people are saying, like, we don't have time to make a code case for Hastelloy, and we're just going to throw in stainless steel 316 and call it good, and we'll throw it away as needed. It's an okay way to get started. I don't think it's a good long-term plan. But I mean, just getting started is probably the most important thing. So I don't know. I'm on board with it.
I mean, again, it sounds like on paper, you can make a case, solves a lot of problems. It's simple, it's shiny, it's new. But then when you actually start to get that real world experience racking up, things get messy and complicated pretty fast. It really struck me. I think it was one of my first interviews with James Krellenstein. He was talking about how, we have been debugging pressure vessels and steam as a working fluid since the 1850s, and lots of lessons learned, lots of iterations. You hosted a recent commentary on What is Nuclear by Ethan Chaliff, I believe his name is, talking about how nuclear iterates very, very slowly. So in any case, it sounds like this is promising, interesting technology worthy of pursuit, but perhaps not something we should be pinning our hopes on for near-term salvation of humanity. And
Yeah, exactly. Like it's just like all these other things. Like it sounds awesome. It's shown promise in reality, and I'm glad people are investing in it now. And like, let's build a couple and let it play. Let's let it compete with the other people making other types of reactors and other power sources. And like, I am really excited to see. I mean, there's a molten salt reactor at Abilene Christian University that is like under construction. It has a construction permit from the NRC. It's a research reactor, but it's a full-on molten salt reactor, it's like a megawatt, and like it's going to have enriched lithium, and it's going to they're trying to find fuel probably by downblending EBR2 fuel. And like they'll learn if it's like right downtown in Abilene, Texas. It's on the campus. And they will learn a lot from that. Like that thing coming online would be awesome. Like we're already behind China because they've got the thing fully constructed. But like, okay, let's get one constructed. TerraPower is doing a critical experiment at INL that's going to be actually nuclear powered as well. So that's something on there. Not the sodium. There's like two TerraPower reactors. There's the Natrium in Wyoming, which is sodium metal with molten salt thermal energy storage. And then there's the molten chloride fast reactor, which uses chloride salts instead of fluorides, which is a whole other thing. And because we've never run a reactor like that, it's like, okay, let's build a little one. And so there's a little one being built or planned at Idaho now that should come on and tell us the basic sort of nuclear physics and dynamics of that kind of a salt for the first time ever. So that kind of stuff, like that's pushing the envelope. And that's exactly what we have to do to find out if all that stuff on paper, it's never going to be as good as it looks on paper, but where you end up is unknown in terms of like how much worse than paper are you. You don't know until you build and operate that thing. And so that's the name of the game. Find a small one, build it, operate it, learn the lessons, and see if you're still excited. And so that's just the name of the game.
All right. Well, I think those are wise words to end on. Nick, thanks for coming back. This is a lot to bite off and chew. So hopefully we've clarified more than we've complicated.
Yeah, I hope so.
A really, really interesting story.
Great.
Thank you.
Thanks for having me on. Always a pleasure.
Cheers.
Take care.